Well, so today we will be discussing the idea of tangent vectors on a manifold. So, this idea of tangent vector is already known to us in Rn setting. So, if you are working in Rn, then we know what vectors are. Let me, for simplicity, let me consider R3. In R3, vectors are usually drawn from the origin O. So, a vector is something which has a sense of direction and magnitude both, but the direction, the notion of direction and magnitude does not make sense in a topological space. So, we will look into its characterizing property. Moreover, we consider all the vectors with their tail at the origin in R3. If you want to consider a vector at some other point, say P, so what you will be doing, you will be translating this vector to the point P, and then you will draw a vector of the same size with tail at the point P instead of the origin O. So, if this vector was x, we call it x sitting at the point P, xp. So, if you want to look, if you want to say the same thing in mathematical notation, you will say if P is a point in R3 and x is a vector of R3, then by xp, the tangent vector at P, you actually mean P plus x. Because you can regard P also a vector. If you add these two vectors, you will be getting this. So, P plus x will be the vector xp. All right. Now, one can see we can in fact define all vectors at the point P. So, I can add vectors. Say if there are two tangent vectors at P, I will add them like this. I will take two vectors of the R3, take their sum, and then you translate at the point P. That will give me the tangent vector at the sum of two tangent vector at the point P. If you have, you can define alpha times xp also. And how will you define? You take vector x, multiply it by the alpha, and you then translate it to the point P. So, these two operations give you the operation of vector space, the addition and multiplication by the scalar. It will satisfy all the properties of vector spaces, and this would mean the set of all tangent vector at the point P in R3 will become a vector space. It becomes a vector space.
P plus x is just a notation, so it is not addition, no, sir? P is a point, x is a vector.
ये translation है. This is the translated. So, I have translated the vector xp to the point P. So, this is the vector xp. All right. So, this is the idea that we already have. Usually, as an example, if you consider a curve in R3 or in Rn, whatever, then we consider the tangent vector at the point P. So, this is xp, the tangent vector. So, if gamma is a curve from an interval I into Rn, so gamma at the point say t0, I pick up a real number from the interval, and this will be some u1 t0, u2 t0, un t0. This will be the point P over here, is it right? Now, what you do, you differentiate this with respect to t and then consider its value at the point t naught, you know it comes out to be u1 dash t naught, u2 dash t naught, and so on, un dash t naught. So, this is the tangent vector of the curve, which can be treated in the same manner. Okay? So, they are sitting at the point. So, the image of t naught will be some point p. So, this velocity vector, this is in fact the velocity vector of the curve. Of the curve gamma.
It is an x piece actually.
Yes, you call it at the point p. So, velocity vector of a curve we already know, but we are just recognizing it as a typical tangent vector of R3, all right, of Rn in general. Okay. Now, same way you can consider a surface and you can draw a vector tangential to the surface. Suppose I draw this tangent vector at the point P. So, this is also a tangent vector in our sense also. Okay, thank you. How will you draw a tangent vector on a surface? You will be considering a curve passing through P. Okay. So, just first forget about the surface. I have drawn a curve over the surface. So, this curve lies on the surface. Then draw a tangent as I did in the earlier case. This tangent vector will be a tangent vector in our sense also. So, a tangent vector to the surface is a tangent vector which is tangential to certain curve passing through that point. Okay. So, this is what we have, and you can realize once again in this case also that the tangent vector over a surface at a point P will form a vector space of dimension 2. All these things are easy to realize. So, what I am going to do now is to discuss these ideas in manifold. So, as I told you that in manifold the problem is you cannot view a vector like this. You have to look for its properties and those properties which characterize it. So, what you do, you consider the space R2, the plane, okay? And suppose you have a point, you have a point or vector. Okay, suppose there is a vector in R2, let me denote it by AI plus Bj. Or you can also identify this vector by A comma B. All right. Now, you define a real valued function f on R2. Okay. Then this gradient of f, or you also write down del f, vector point. I can, this is a vector which can be written as del f upon del x I plus del f upon del y j. Or you can also identify this vector with the pair del f upon del x, del f upon del y. Okay. Now, this in a plane you can see the vector is a comma b. So, this vector is a comma b. You may call this point as P. So, P is the name of this point, which is in fact the head of the vector.
Yes.
Okay. Now, what I will do, I will consider the tangent vector xp, this is xp, or you can draw it over here. Okay. This is the tangent vector xp. Same direction. XP. This is p. Okay, so xp is a comma b. Del f is this vector, so I will consider xp dot grad f. Okay, I am taking the dot product of these two vectors, this one and this one. So the dot product of these two vectors will be a times del f upon del x plus b times del f upon del y. So look here, I can consider this quantity xp dot del. Gradient is an operator. Okay, so I can consider, instead of writing xp dot del f, I will write it down like this: xpf equal to a times del f over del x plus b times del f over del y. अगर मैं ये नोटेशन इख्तियार करूं तो इसको गौर से देखें ज़रा, तो आपको ये महसूस होगा कि xp is a kind of an operator which operates on function and gives you this quantity which is a real number, because these derivatives are computed at the point p. All right. And moreover, we know that as these del upon del x and del upon del y, they satisfy Leibniz property, they will satisfy the Leibniz property. Both the partial derivative are linear by nature and they satisfy the Leibniz properties. So I can regard my vector, instead of saying that this is a directed line segment, I will rather say it. So we can view xp as a map which operates on what? On differentiable functions. So the space of differentiable function is C infinity p. Okay? And the values are in R, and what xp does, it picks a function and associates a real number xpf, and this xpf satisfies the linear property and the Leibniz property. Number one, if you operate xp on the sum of two functions, or rather some alpha times f plus beta times some other function g, it will be alpha times xpf plus beta times xpg. और अगर आप इसको देखें तो ये राइट साइड से पता ये चल रहा है कि xpf इज़ द डायरेक्शनल डेरिवेटिव ऑफ f. जो डायरेक्शनल डेरिवेटिव है वो है ये राइट साइड में, और कुछ नहीं है. तो डायरेक्शनल डेरिवेटिव की प्रॉपर्टीज़ हमें पहले से मालूम है कि वो लीनियर होता है और इसके अंदर लाइबनिज़ प्रॉपर्टी होती है. उसको मैं पिक कर लेता हूँ एंड डिफाइन माई एब्स्ट्रैक्ट टेंजेंट वेक्टर as a operator which operates on functions and produces real number satisfying these two properties. xp of f into g is also meaningful because this is the space which is an algebra. यहाँ पे functions को जोड़ा भी जा सकता है, functions को स्केलर से भी मल्टीप्लाई किया जा सकता है और दो फंक्शन को मल्टीप्लाई भी किया जा सकता है. तो ठीक है ना, ये फैसिलिटी चूँकि यहाँ पे है, तो आवर डोमेन स्पेस इज सी इन्फिनिटी पी. This is xpf into gp plus xfp into xpg. Okay. So we have picked up these two properties to define an arbitrary tangent vector on a manifold. Now I am in a position to write down the formal definition. Okay. So now I am going to assume that M is a smooth manifold of dimension n. So let M be a smooth manifold of dimension n. And P is a point in M. I have picked up a point in M. C infinity P is the algebra of C infinity functions on M. Then a tangent vector xp at P is defined as a map. It is not a directed line segment, it is a map. What is this map? This is a map from C infinity P to R, satisfying property number 1 and 2, satisfying the properties 1 and 2. That's all. This is the definition of a tangent vector. तो टेंजेंट वेक्टर मैनीफोल्ड के ऊपर किसी पॉइंट पे एक डायरेक्शनल डेरिवेटिव का जनरलाइज्ड वर्जन है। दिक्कत बेसिकली ये थी कि यहाँ पे वेक्टर्स लाइन सेगमेंट के तौर पे नहीं डिफाइन किया जा सकता, उसको रियलाइज़ नहीं किया जा सकता। इसी वजह से हमको डायरेक्शनल डेरिवेटिव की तरफ माइल होना पड़ा। डायरेक्शनल डेरिवेटिव में आप बोले ना बोलें, एक डायरेक्शन का सेंस है तो वो सेंस उसकी प्रॉपर्टीज़ में घुल गया और हमको वो ऑब्जेक्ट मिल गया और हम उस लैंग्वेज में बात कर रहे हैं विच मेक सेंस ऑन अ मैनीफोल्ड। ऑलराइट, ओके, ऑलराइट, नेक्स्ट आई विल डिस्कस सम एग्जाम्पल्स ऑफ ए टेंजेंट वेक्टर। तो जो पहले बात देखने की ये है, ये तो मैंने आपको मोटिवेट कर दिया कि ये प्रॉपर्टीज़ कहाँ से आई, लेकिन अगर आप इसे किताब में कहीं पढ़ेंगे तो डेफिनेशन ये लिखी होगी, एंड मोस्ट ऑफ द पीपल विल नॉट रिकॉग्नाइज इट एज ए टेंजेंट वेक्टर। ओके, दे मे रिकॉग्नाइज इट एज ए जनरलाइज्ड वर्जन ऑफ द डायरेक्शनल डेरिवेटिव। So what I want to tell you that the typical tangent vector that we are familiar with, are they behave as tangent vector of the manifold? The answer is yes. Our irregular curve is a differentiable manifold of dimension 1. Is it right? A regular surface is a differentiable manifold of dimension 2, and we know they are tangent vectors. Okay, so now we will look to those tangent vector and will realize that they satisfy the same characterizing properties. Is it right? So first let us start with the tangent vector of a curve.
So magnitude we can also find same as we can find the magnitude of vector in R.
Magnitude, you see, if you are in R3, magnitude is determined through A and B, the components of the vector.
Yes.
So we have taken note of that. सो मैग्नीट्यूड तो ए और बी से आता है, उसके कंपोनेंट्स A1, A2, A3, AN से आता है, तो वो इसमें शामिल होता है। तो मैग्नीट्यूड भी है उसमें कुछ, लेकिन नाम नहीं ले रहे हैं आप। आप ये कभी मत बोलिएगा कि टेंजेंट वेक्टर का इतना मैग्नीट्यूड है और ये डायरेक्शन है, ये दोनों बातें मीनिंगलेस होंगी मैनीफोल्ड। ठीक है, ओके, व्हाट आई वाज टॉकिंग, आई वाज सेइंग about the tangent vector of a curve. So let me first of all, how will you realize a curve on manifold? So a curve, I have to write down the definition of a curve on a manifold. A curve on a manifold, a curve on a manifold M passing through a point P, passing through a point P, P in M is a map. So throughout I am assuming then M is a differentiable manifold of dimension n. ये बात throughout हम assume करके चल रहे हैं. So it's a map, a curve gamma, उसका नाम रख लीजिए gamma. So gamma I am treating as a map from minus something epsilon to plus epsilon into M. Okay. So if I choose a point over here, say 0, so gamma 0 will be a point in M. You may call it P. Okay. If this is the situation, I will say gamma is a curve passing through point P of M. So M is a point over here, M is a manifold over here, gamma is a map which takes this interval over here. Suppose 0 is somewhere over here. So the image of this interval will be a curve like this. It will pass through the point gamma 0, which I am calling as P. Okay. So the tangent to the curve gamma, the tangent, it's a continuous map. Yes. You can take a differentiable map also. No problem, because you understand the meaning. So the tangent vector to gamma at P is gamma 0 is what? अब डेरिवेटिव as such नहीं करेंगे. What I will do, I will consider a real valued function over here. Suppose f is a real valued function defined in the neighborhood of P, not necessarily on M, on of whole M. You can consider a function which is differentiable in a neighborhood of P. Okay. And this curve I am taking as a smooth curve. Okay. Now you just compose these two maps. This is F composition gamma. So F composition gamma is a map from this interval into R. Okay. What I will do, I will differentiate it. I will differentiate this F composition gamma at t equal to 0. Whatever you will be getting, I will call it gamma dash 0 of F. Now this fellow gamma dash 0 I will call as a tangent vector. ये अभी तक गामा डैश 0 का सेंस आपको मालूम था Rn में. ठीक है. अब ये मेरा सिर्फ एक नोटेशन है और जानबूझ के ये नोटेशन हमने चूज़ किया है ताकि आप इस गामा डैश 0 को और अपने पुराने वाले गामा डैश 0 को देख सकें कि दोनों सेम ही ऑब्जेक्ट है. ठीक है ना. So the tangent vector to gamma at P, say gamma dash 0, tangent vector gamma dash 0 to gamma at P is defined as gamma dash 0 operating on F. I am defining it as d by dt of F composition gamma at t equal to 0. ठीक है.
So this t is equal to 0 is necessary to defining tangent vector?
नहीं, आप कुछ भी ले लें. कोई भी पॉइंट ले सकते थे, ज़ीरो पे कंप्यूटेशन आसान हो जाती,
That's why we are
दैट
taking
इज,
this.
अदरवाइज इट डजंट मेक एनी, इट्स नॉट इम्पॉर्टेंट, ज़ीरो इज़ नॉट वेरी इम्पॉर्टेंट, फॉर आवर कन्वीनियंस आई हैव चोजन इट लाइक दिस. ओके,
So because we have defined tangent vector manifold through a map to R, that's why we just took it to R and then we defined it this way.
yes,
Because
Sir,
that
is
is
it the regular curve for at every point which is different?
regular means non-zero and differentiable.
Different.
First derivative should be non-zero. Yeah, this is the meaning that we have.
This is the particular at point 0.
This is, yes, this is differentiable at p.
तो ऐसा लेकिन वो particular होती है ना, मतलब एक जीरो पे लेके हम किसी भी पॉइंट पे ले सकते हैं.
किसी भी पॉइंट पे ले सकते, किसी भी पॉइंट पे ले सकते. Okay. So now we will check whether gamma dash 0 defined in this manner is a tangent vector of the manifold at p. So the answer is yes. We only have to verify. So let us verify that gamma dash 0 is a tangent vector at p. This is the verification of the fact that gamma dash 0 is a tangent vector at p. So first of all, it should be a map from the space of functions into R. That you can easily see from here. You see, I have written like this, it operates on f and the element in the right side is a real number. जब आप f कंपोजिशन गामा को डिफ्रेंशिएट करोगे विद रिस्पेक्ट टू t और उसकी वैल्यू एट t इक्वल टू 0 पे निकालेंगे तो वो रियल नंबर ही आएगा. तो एक बात तो यहाँ से साफ दिख रही है कि गामा डैश 0 is a map from C infinity p to R. That's an obvious thing to realize. The other things we have to check. The first property, defining property is that gamma dash 0 of f plus g. ये देखना पड़ेगा आपको. So let us see. By definition, it is equal to dy dt of f plus g composition gamma and evaluated at t equal to 0. This will be equal to, now you are working on a functions from R to R. So dy dt की प्रॉपर्टी मालूम है, वो अभी यूज़ करेंगे, पहले इसको कंपोज कर लें. सो दिस विल बी f composition gamma plus g composition gamma at t equal to 0. This is easy.
Yes.
Next, the property of dy dt. It says when you differentiate the sum of two functions, it is the derivative of the first function plus derivative of the second at t equal to 0. The first term is nothing but gamma dash 0 f. The second is gamma dash 0 g. Look at the box relation. So we have checked that gamma dash 0 f, f plus g is gamma dash 0 f plus gamma dash 0 g. So first property holds. On the same lines, you can also check, that will be still easier, that gamma dash 0 operating on some scalar time of function f. That is easy to see that it is alpha times gamma dash 0 f. Combining first and second, you will say that gamma dash 0 is a linear map. On where? On C infinity p up to R. Now the third property is the Leibniz property. So I will start with the product of two functions f into g. Here f and g I am choosing from C infinity p. That is understood, okay? And now by box definition, it will be equal to gamma dash, dy dt of f into g composition gamma at t equal to 0. And that is easy to see. It is f composition gamma into g composition gamma at t equal to 0. Okay? And now dy dt we know satisfies the Leibniz property. It's a map on functions of R and it satisfies the Leibniz property. तो राइट साइड बन जाएगी dy dt of f composition gamma at t equal to 0 into g composition gamma at t equal to 0, okay, and plus f composition gamma at t equal to 0 into dy dt of g composition gamma at t equal to 0. Now look at the box relation. This quantity is precisely gamma dash 0 f. This quantity g composition gamma at 0, यही है ना? तो इसको आप लिखेंगे g of gamma of 0, यही लिखेंगे ना? गामा 0 का नाम आपने p रखा है तो ये gp हो गया. So this is gp plus same way this is fp and this quantity by box relation is gamma dash 0 operating on. So now left hand side is gamma dash 0 on f into g, it is equal to this much, means the Leibniz property holds. So gamma dash 0 is a tangent vector at p. So this implies gamma dash 0 is a tangent vector at p. Okay. So we know that these vectors which were already known to us are tangent vector in our sense also. Then if you have example number 2, if you consider around P a coordinate system, say xi. So if xi is a coordinate system, जब हम कोऑर्डिनेट सिस्टम बोलते हैं तो उसका मतलब ये होता है कि x1, x2, x3, xn they are real valued functions defined on the neighborhood of P. So is a coordinate system on a neighborhood around P. Okay. अगर xi coordinates हैं around a point P, then we defined what do we mean by del upon del xi at P. ये हमने शायद define किया हुआ है. And how did you define it? We define it like this. हमने define किया था partial differentiation on manifolds, okay, with respect to these local coordinates, and we define it like this. क्या था? Del of what? Del of f upon f composition. f देखिए ये है ना, ये फंक्शन f है, ठीक है, और xi क्या है? कोऑर्डिनेट सिस्टम है. तो आप यहाँ से कहाँ जाते हैं? Rn में जानते हैं थ्रू फाई, ये Rn में आ गए. Rn से कहाँ जाते हैं? ui के थ्रू r में आते हैं. तो दोनों को एक साथ कंपोज करें तो क्या हो जाएगा? ये xi हो जाएगा, इसे ui कंपोजिशन फाइन. ठीक है. सो व्हाट यू डू इज, तो यहाँ से फंक्शन अगर लें आप, ये R में है, so this is F composition phi inverse. F composition phi inverse को आप UI के रेस्पेक्ट में डिफरेंशिएट कर सकते हैं, because these are functions from R into R. So what you do, you differentiate F composition phi inverse with respect to UI. At what point? At the point phi p. अब यहाँ phi inverse लगा तो ज़रूर दिया है आपने, लेकिन आप ये रियलाइज़ कर चुके हैं कि इस phi से कोई फ़र्क नहीं पड़ता। अगर वहाँ पे कोई दूसरी कोऑर्डिनेट नेबरहुड भी है जो इसके साथ ओवरलैप कर रही है, तो उन कोऑर्डिनेट के रिस्पेक्ट में भी यही वैल्यू आएगी। ओके, सो दिस इज हाउ यू डिफाइन पार्शियल डिफरेंशिएशन विद रिस्पेक्ट टू xi। ओके, अब ज़रा गौर से देखिए, नाउ यू विल रियलाइज वंस अगेन दैट द वे आई हैव रिटन इट लुक्स एज इफ डेल अपॉन डेल xi आर ऑपरेटर्स, they operate on functions and produce real numbers. Okay, so whether these operators on functions are tangent vector or not, that needs to be checked, and that I will be checking. So once again, verification of the fact that del upon del xi's are in fact tangent vectors to the manifold at the point P. So my claim over here is that del upon del xi, with this understanding in mind that xi's are the local coordinates around P, then del upon del xi are tangent vectors at P. Del upon del xi at P are tangent vectors. At P. This is my claim which needs verification. तो फिर वेरिफिकेशन में दो ही पॉइंट हैं जो वेरीफाई करने के हैं, लीनियर प्रॉपर्टी एंड लाइबनिज। लीनियर प्रॉपर्टी को आप दो स्टेप में वेरीफाई करते हैं। तो पहले आप डेल अपॉन डेल xi को ऑपरेट कीजिए ऑन द सम ऑफ टू फंक्शन से f प्लस g आई एम पिकिंग फ्रॉम C infinity P. So I have picked two functions f and g from here, and then I will apply this definition. This is the definition of partial derivative with respect to xi. So it will be del upon del ui. What about del ui's? F plus g composition phi inverse. ये ui's क्या है? ui's are the natural coordinates of Rn. वो ये ऑर्डिनरी पार्शियल डिफरेंशिएशन है Rn का, जो जिसके बारे में जानते हैं कि इसके अंदर लीनियर प्रॉपर्टी भी है, इसके अंदर लाइबनिज प्रॉपर्टी भी है। सो इसके टर्म्स में लिख दिया तो ये बात वैसे भी क्लियर हो गई। फिर भी देख लेते हैं। तो ये फाई इनवर्स के साथ जब कंपोज करेंगे आप, तो ये हो जाएगा f कंपोजिशन फाई इनवर्स प्लस g कंपोजिशन फाई इनवर्स, एंड एवरीथिंग इज बीइंग डन एट द पॉइंट फाई p. Okay, so by the additive property of del upon del ui, it is del upon del ui of f composition phi inverse at the point phi p plus del upon del ui of g composition phi inverse at the point phi p. Now look at this box relation. This was box number 2. You will notice that the first thing is what? Is del upon del xi of, कहाँ यहाँ लिख दे? Oh, the first term in the right side is del upon del xi at p operating on f. The second term of the right side is del upon del xi at p operating on g. So the first part is verified for the linearity. In the same manner, the second part can also be checked, that del upon del xi at P operating on alpha f is equal to alpha times del upon del xi at P on f, on the same manner. And thirdly, the Leibniz property, that is del upon del xi of product of two functions, that I am leaving as an exercise for the students to check themselves. So that will be del upon del xi of f at P, so this is at P, into Gp plus Fp into del G upon del xi at the point P. So after these two verifications, you will say that the del upon del xi is also a tangent vector at P. Okay. So these are the two natural examples of tangent vectors. So as in Rn, you had seen the set of all tangent vectors at a point P of a manifold must satisfy must be a vector space. Okay, ये बिल्कुल ऐसे ही मामला है कि जैसे मैं कहूँ कि set of all tangent vectors on a surface is a plane.
At a point.
Yes. If you consider the totality of all tangent vectors at a point P of a surface, then it will be the tangent plane of the surface. Set of all tangent vectors to occur at a point will be lines.
Yes.
Is it right?
Yes.
So they are one-dimensional vector space. So in general, if you have a higher dimensional object like a manifold, then we expect that the set of all tangent vectors must be a linear space of dimension n. Okay. So I will be denoting by the symbol TPM. P is a point on the manifold, M is a differentiable manifold that we have already written. So this is the set of all tangent vectors. Set of all tangent vectors to M at P. Okay? ये सेट मैंने ले लिया जिसमें सारे टेंजेंट वेक्टर भर लिए. अब हमारा क्लेम ये है कि इट विल बी ए वेक्टर स्पेस of dimension n. To prove this, I need to define two operations on this set, the addition and the multiplication by scalars. So let me define the sum. So first of all, to prove your assertion, you need to define two operations. Define the sum of tangent vector. Define the sum of tangent vectors as follows. I will pick two vectors, arbitrary vectors in TPM, and will define the sum as xp plus yp. Tangent vectors on manifolds are operators on function, so they must operate on functions and it must give some real number. So I define like this, xpf plus ypf. This is the sum that we propose. ये एक natural sum है of two tangent vectors, and we hope it will satisfy all the properties of the group, axioms of the group. One can check that पहली बात तो यहाँ पे ये दिख रही है कि it's a candidate for a tangent vector because it operates on functions and produces a real number. The two objects in the right side are real numbers. XPF, YPF both are real number. This sum is the sum of two real numbers. This sum is the sum of two tangent vectors. सारे sums को हम एक ही symbol से denote करते हैं, but you understand the meaning. One can check that XP plus YP belongs to TPM. ठीक है ना, पहले तो ये होना चाहिए. ये कैसे प्रूव करेंगे कि ये दिस हैपन्स? Yes. So in order to check that XP plus YP is in fact a tangent vector, I need to check. We need to check XP plus YP operating on alpha F plus beta G. Alpha beta are scalars. Fg are real valued functions defined in the neighborhood of P. So I must prove it that it is XP plus YP alpha times F plus beta times XP plus YP. और दूसरी बात, we need to see that XP plus YP operating on the product of two functions Fg. It should be equal to XP plus YP operating on F into GP as it is plus FP as it is into XP plus YP operating on G. ये दो वेरिफिकेशन करने के बाद ही आप ये कह पाएंगे कि XP plus YP belongs to TPM. तब आप पहला स्टेप होगा आपका कि this addition is a binary operation. So having done this, you will say that addition is a binary operation. On TPM. एक ही बात है, उसी बात को अलग ढंग से कहा मैंने. ओके, अब इसको मैं एडिशन कह रहा हूँ तो इसके अंदर सारी एबिलियन ग्रुप वाली होनी चाहिए प्रॉपर्टी. अब नेक्स्ट अगला नंबर क्या होगा आपका? Associativity. Now you pick three tangent vectors XP, YP, take three vector XP, YP, ZP in TPM. That was the first step. This is the second step that I am doing. I will take the sum of these three tangent vector like this. Then I will take the sum in this manner, YP plus ZP, and then check that these two sums are same for any three tangent vectors at P. जैसे ये बात चेक हो जाएगी, आप कहेंगे yes, associativity holds with respect to the binary operation. तो ये चेकिंग जो है वो आसान है. I hope it can be done easily by anybody. And number 3, I have to search out an element of the type 0 जिसको आप ज़ीरो टेंजेंट वेक्टर कह सकें. ठीक है, जो इसकी आइडेंटिटी की तरह बिहेव करे, एडिटिव आइडेंटिटी की तरह. सो वी प्रपोज अ मैप 0. Consider a map which you denote by 0 from C infinity P to R. ठीक है, और हम इंट्यूशन से इसको डिफाइन करेंगे कि दिस इज a map which operates on any function gives you the scalar 0. This is the 0 function, this is the scalar 0. Now पहले तो ये जो 0 या O है, whatever it is, ऑपरेटर ही है. इसका नाम मैंने O या 0 जो भी कहा वो रख दिया. ठीक है ना, ये दिस इज एन ऑपरेटर. सो आई नीड टू चेक कि येस इट्स ए टेंजेंट वेक्टर. जो चीज़ लिखी है उसको टेंजेंट वेक्टर तो होना पड़ेगा ना. सो हाउ विल यू शो दैट दिस इज ए टेंजेंट वेक्टर? अगेन दोज two properties? So 0 satisfies, this O satisfies number 1 and number 2. These are the two characterizing properties of the tangent vector. अगर इसने ये कर दी तो आप इसको admit कर लेंगे कि yes, it's a tangent vector. So this would imply that this O belongs to TPM. ठीक है? After this you will check कि whether for any function, whether for any tangent vector xp, this condition holds or not. xp plus 0 equal to xp. For any tangent vector xp, this condition holds. So once you have admitted it as a tangent vector, you can add it into any other tangent vector xp. This holds. How will you show that this holds? Operate the whole thing on a function, and you will see you will be getting same as xpf. So that will prove that 0 is the additive identity. ये verification करने के बाद you will say कि this 0 is the additive identity of TPM. It has an identity also. And lastly, you will search a inverse of a tangent vector, additive inverse of a tangent vector. And we propose for xp, this is number 4. For xp in TPM, consider an object minus xp. मैं शुरू से ही उसको minus xp से denote कर रहा हूँ, ठीक है? And I define it like this, minus xp f, I am defining like this. This is the definition of minus xp. It is xp f, and this is a real number, I will put a minus sign. This is the definition of minus xp. अब जो आपने definition propose की है intuition से, उसको अब देखना पड़ेगा कि वो वाकई में tangent vector है या नहीं. It is a tangent vector. Once again, the two characterizing properties will tell you कि yes, it's a tangent vector. That verification I am leaving. These are simple things. So minus xp, one can see belongs to TPM. Okay, once it belongs, it must satisfy the properties of additive identity. Then you have to check. Check that minus xp, when it is added with xp, it gives me the value. It is the 0, which 0? This additive identity. This is a matter of checking. तो फिर क्या करेंगे, हम इस सम को फंक्शन पे ऑपरेट करेंगे और देखेंगे हमारा आंसर 0 आता है या नहीं आता. ओके, सो दैट विल शो दैट इट्स एन आइडेंटिटी. सो दिस इम्प्लाइज, ये सारे चार चीज़ें देखने के बाद और एक चीज़ और देख लें नंबर 5 पे, दैट कम्यूटेटिविटी या अबेलियन प्रॉपर्टी ऑल्सो होल्ड्स yp plus xp for all xp yp in TPM. After doing all these things, you will say that TPM is an abelian group. So we will not stop at this point. We will learn what is the multiplication by scalars. So if I pick a tangent vector from TPM and multiply it by scalar alpha, whether I get a tangent vector or not. The answer is yes. You have to define properly the multiplication by scalars. So in the next step, I will pick a real number alpha, and I will pick an arbitrary tangent vector also, and we'll introduce alpha xp. This is a new object, and this object I will define as an operator on functions, and the proposed definition is that you consider this real number and you multiply this real number by alpha. ये real number है और ये भी real number है. So multiplication of two real number is a real number. So this object is such such that when it operates on a function, it produces a real number. ठीक है? So this implies that alpha xp is a map from C infinity p to R. Okay. So to show that it belongs to TPM, we must verify those two properties. Also, alpha xp satisfies number 1 and number 2, the two characters property, and which implies that alpha xp is a member of TPM. So not only you have a binary operation, you have an external operation also. And once you have more than one operation, you must check the compatibility. So we should also check, at this point we should also check that alpha plus beta times xp is equal to alpha xp plus beta xp. Number 1, this is called distributive property. There is another distributive property. You take the sum of two tangent vectors and multiply it by a scalar alpha and see that it is equal to alpha xp plus alpha yp. The two distributive properties hold. Okay, there is a real number 1. आप रियल लाइन पे काम कर रहे हैं तो देयर इज ए रियल नंबर 1. 1 इंटू एक्सपी इज सेम एज एक्सपी. स्केलर मल्टीप्लिकेशन से फॉलो हो रहा है. राइट साइड में 1 से मल्टीप्लाई करेंगे तो वही रहेगा. सो दिस प्रॉपर्टी इज ऑल्सो वन ऑफ द इम्पॉर्टेंट प्रॉपर्टीज एंड दैट्स ऑल. ठीक है, वो भी इजी है. अल्फा बीटा, you multiply the two scalars alpha beta and then you multiply this product by xp for any xp and you will see that it is alpha times beta xp same as beta times alpha xp etc. ठीक है, ये सारी प्रॉपर्टीज वेरीफाई करने के बाद आप ये बोलेंगे कि TPM इज़ ए रियल वेक्टर स्पेस. ओके, सो जो बात मैंने शुरू में कही थी कि दिस स्पेस ऑफ ऑल टेंजेंट वेक्टर मस्ट बी ए लीनियर स्पेस, बिकॉज हमने देखा है कर्व के केस में, सरफेस के केस में, कि हमें एक टेंजेंशियल प्लेन या टेंजेंशियल लाइन मिला करती थी. तो यहाँ पे हम एक्सपेक्ट कर रहे थे कि कोई लीनियर स्पेस ऑफ डायमेंशन n मिलना चाहिए. द आंसर इज़ दिस एंड द कैंडिडेट इज़ द TPM. ठीक है, अब अगली जो बात है वो ये है कि ये फाइनाइट डायमेंशन का है. दैट शुड बी रियलाइज्ड वेरी इजीली, और इसकी कोई कैनोनिकल बेसिस भी हमको निकालनी पड़ेगी. ठीक है, बेसिस तो वेक्टर स्पेस की एक तो होती नहीं है, लेकिन देयर आर सर्टेन बेसिस विच वी कॉल देम कैनोनिकल बेसिस. सो वी विल सर्च कैनोनिकल बेसिस फॉर द टेंजेंट स्पेस. दैट वी विल बी डूइंग इन आवर नेक्स्ट लेक्चर. I stop at this point.